Not sure what time it is, though. Not sure what time it is where you are, people, but anyway, welcome back after the break. And our first speaker in this session is Pankaj Kumar Manjhi, who will be talking about moles and Frobenius groups. Take it away.
Okay, good morning in India and in your country, I think it is afternoon. So this is my topic, mutually orthogonal Latin square mid-moles from Frobenius group. So the outlines of my presentation is like this: abstract, then definitions of Latin square, mutually orthogonal Latin squares, Frobenius group, and after that the method that how we construct moles from Frobenius groups. So ultimately in this presentation, we will see a method of construction of moles with the help of suitable or every Frobenius group actually. Latin square already we know in the previous session that an n by n array filled with n symbols in such a way that each symbol occurs once in each row and each columns is a Latin square. And just for example, these are the Latin squares. And moles are simply the collections of Latin squares. So that if we superimpose one Latin square into the another, then we get all the pair exactly once, like this. This pi 1 and pi 2 are the two Latin squares, and they are actually mutually orthogonal, since if we superimpose one into the another, then we get all the pairs of symbols exactly once. So these are the some facts about the moles. There can be at most n minus 1 Latin squares of size n in a set of moles. A set of n minus 1 moles exists if n is prime number. It is already you would know that the collection of moles is at n minus 1 when n is prime number or prime power. There exists a set of n minus 1 moles in prime power also. This is the third one. And this is the theorem, Nis theorem, that minimum number of Latin square is given by except 1 known to be for all x. If there are r moles of order m and a set of r moles of order n, then there is a set of r moles of order mn. These are the known results, and that is we can write like this in symbolically: n mn will be minimum of nm comma nn. And 6 number is the prime factorization of n, then it will be greater than minimum of this. So actually in my topic of this presentation, let me define Frobenius group. A group is called Frobenius group if it has a proper subgroup H having this property that its intersection with x inverse hx for all x in G minus h will be the singleton one which contains identity only. This subgroup H is called Frobenius complement, and K is actually Frobenius kernel. I later define the K. Actually, this Frobenius group G is a semi-direct product of K and H, and this K is a subgroup which is called Frobenius kernel. Some examples: this is the alternating group F4, and in this group we have the kernel generated by these two elements 1, 2, 3, 4 and 1, 3, 2, 4. S3 is also a Frobenius group. In this group, the kernel is the cyclic group of order 3 generated by 1 to 3, and H, that is Frobenius complement, is 1, 2. So Frobenius, these are we cannot say that are unique. H maybe we take 1, 3 or 2, 3. Every dihedral group with n prime is also a Frobenius group, and in this Frobenius group, the kernel is simply A. As we see the dihedral group like this, AB generated by A and B. A is order of A is n, and order of B is 2, and A and B are related like this, that AB equals to BA inverse, and in this group the kernel will be this generated by B actually. That is cyclic group. Both are the cyclic groups. So this is another example of Frobenius group. This is in matrix form. Let us write in 2 by 2 matrices like this, where GFPN stand for the finite field of order p raised to the power n. So G is given by this set, and this is a field of order p raised to the power n, p is some prime. Then the Frobenius group, if we like this, then this group is actually of order p raised to the power n into p raised to the power n minus 1, and the kernel for this group will be given by the third one, and fourth one gives complement. And some interesting fact about the Frobenius groups are actually most interesting results or representation of Frobenius group in their permutation representation. So their permutation representation, we can say Frobenius group are transitive, and the stabilizer of any point may be taken as the Frobenius complement. So complement, there are many complements for any Frobenius group. Let H be the Frobenius complement of H. Then what is important in third is that G act on G by H by left multiplication, and this action actually gives rise to the permutation representation of G. The Frobenius complement is unique up to conjugation. The kernel and the Frobenius H, and is semi-direct product of K and H. So this is the important result about the representation of Frobenius group. Let G be a Frobenius group and H be its complement. Then the action of G on the collection of left cosets H may not be a normal subgroup of G, but here K is normal subgroup of G. So this collection of left cosets G by H is not necessarily a quotient group, but the action of the elements of G on the left coset on G by H by a left multiplication gives a faithful permutational representation of G, and this permutation representation has the property that there is at least one non-identity element with a fixed point. And this is the theorem given by me a few years back, that if G is some Frobenius group and K is Frobenius kernel with it complements H, and then we must have order of H. Order of H is number. OH means order of H moles, and each of order of K. So the method from this theorem is like this. Let G equals to HK be a finite Frobenius group, where H is complement and K is kernel. And let these are the permutational representation of H and K. The permutation representation is actually obtained via the multiplication of the elements of G on the left coset of G by H. And these are the permutational matrices actually. So we can say the matrix representation of these permutations. So ultimately we identify H and K by these two sets. Then it is easy to see that this summation for number gives us moles for every j equals to 1, 2, 3, dot, 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 r. I just illustrate this method. Suppose G is this group 1, 2, 3, and 1, 2 generated by these two elements, and in this case H kernel is like this, the complement is like this, and kernel is like this. Then MH1, MH2, MH3, these are the matrix representation of actually these elements of H. And MK1, MK2, MK3, MK4, these are the matrix representation of elements of K respectively. Then we have these three moles, each of order 4. So we get all the moles, class of moles by this method also. So this is the illustration, and we can verify the result. And these are the references. Actually, this theorem I have already proved 5 or 3 years ago, but that is not available in internet, that published in national journal. So I think that's why I want to represent this one, so that researcher may know that Frobenius group and moles are actually connected. So this is my presentation. Thank you. Now I am waiting for some questions.
Okay, thank you